For sure, for sure. Again, visual aid would be great here, but hopefully by now people can at least visualize in their head this graph that is growing. So each transaction that is issued in a network references 2 previous transactions in the network. And again, those 2 transactions, of course, reference their own respective 2 transactions and so on and so on and so on, right? So when you issue a completely new transaction, that is, of course, not confirmed yet because no other transactions is referencing it. So these transactions that are being referenced are again being referenced by some other new transactions. So as more new transactions occur, they indirectly get referenced more and more and more and more. So you have this random walk Markov chain Monte Carlo algorithm that you run, this tip selection algorithm as we call it. When you run that tip selection algorithm, you can see how much of the network is referencing your transaction. So for instance, if you run it 100 times and you see that 50% of the times that you run it, you have 50% of the network confirming it, you may not want to accept that transaction yet. So you have this heuristic, just like you have in blockchain, where you don't accept a transaction until there's been 3 blocks confirming it. It's the exact same thing in IOTA.
What about, say I spin up 1,000 nodes or 1,000,000 nodes on my computer and I just flood the network with transactions that confirm a double spending transaction, essentially?
Okay, so this is why we have a small amount of proof of work involved in the transaction. The reason for that is exactly what you're saying here, this anti-Sybil mechanism, this attack mechanism. So if you were to set up, let's say you set up 10,000 nodes, first thing you would have to do was to find other nodes to connect to, like genuine nodes to connect to. That would take you ages to get 10,000 nodes to actually have other neighboring nodes that are honest, genuine nodes. So that's the first hurdle that you would have to overcome. The second one would be the proof of work, that you actually carry out this proof of work on the 10,000 nodes, which would be extremely expensive compared to whatever you were trying to attack. But even if you were to attempt this attack, and even if you get all of these nodes set up and you get to connect to all of the network, you still would not be able to disrupt the network. Theoretically, you may be able to attack some edge node that is not referenced by the rest of the network, like a small partition or something. But in reality, what would happen is simply that your fake transaction, so to speak, would strengthen the rest of the Tangle. So this actually happened 2 days ago, that someone tried to attack the network with 300% hashing power. And all that happened was Tangle absorbed it and the network got more secure and more efficient. So the Tangle is inherently resistant to such attacks. Actually, we encourage spam on the network because it strengthens the network.
It seems like you would need the network to be so huge, you would need so many connected Internet of Things devices in order to defeat the mining power of a single shed in Iceland, you know?
Yeah, no, I completely understand the concern. So in order to kind of elucidate this further, so at the moment we are having this checkpointing coordinator that is just making sure that the network isn't being attacked by this 31% that all distributed ledger consensus is susceptible to. And this is what we call training wheel period. Just like Satoshi set up his first miners, just like the Ethereum core set up a lot of miners in the beginning just to get the network rolling. So that's the current state. So at the moment, this coordinator would simply not give checkpoints to these malevolent transactions. But to answer your questions in regard to like when the coordinator is shut off, which is of course the entire goal, to have a completely running network that is self-sustainable. The issue is that it seems like it would be very easy to attack the network with, like you said, a small database. But in reality, it isn't like that, because the way that we perceive this is that each individual IoT device will have a application-specific integrated circuit, i.e. an ASIC, for hashing of the IOTA hash function. So I have to reiterate or emphasize here that this hash function and the hasher is not like in Bitcoin. So it's a lot more like hash cache than the hashing you do in Ethereum and Bitcoin for mining. It's nowhere near as intensive. So it's not like this ASIC would be huge. It would be a few thousand logic gates. Like it wouldn't add any extra cost or space requirement to any chip. So this means that you attacking from a a regular database with regular processors would have absolutely no chance, because this is so many hundreds orders of magnitudes more efficient than a regular processor or a GPU that it simply would not work.
But also, we're talking about adding a new hardware component to IOTA-enabled devices.
Yeah, exactly. So that is definitely part of the vision here. Like, in order for the Internet of Things to actually have a distributed ledger for payments and data integrity, you need to accommodate this in the hardware. And this seems excessive, and it seems like a big assumption to assume that the hardware manufacturer will take this into account. But then you start to think about it, like, why wouldn't they? Like, this is the new age of technology. Like, you have to accommodate for it, or else your processors become obsolete. It's just like back in the 80s and 90s, you had this dedicated floating point unit processing element that was put into the processors in order to do these floating point math calculations. And as that became a standard, they simply integrated it. Today, it's a complete regular part of the processor. No one even thinks about it. Or let's take another more perhaps simple example to get your head around. Think about mobiles. Let's go back to the 90s and the beautiful Nokias and the early 2000s with the indestructible Nokias. Back then, you didn't really have a lot of graphics to display. So you could run this on the regular microprocessor that was within a mobile. But as the user interface grew, as the user experience demand grew, and gaming complexity, etc. grew, then of course you integrated a graphic processing unit into the system of chip. It's just how hardware has always evolved to accommodate the software. Software is always a step ahead of the hardware in this regard, because that is what drives what is underlying the hardware. What are the use cases? And if we want this payment settlement mechanism between machines, if we want to be able to guarantee data integrity from data generated by sensors, etc., there is no choice but to have a dedicated component to do this. And again, I want to reiterate that it's not like an ASIC that most blockchain enthusiasts would think of, because we, in the blockchain realm, we are used to seeing ASICs as these huge mining rigs, like these expensive, insanely energy consuming circuitry, but that's not the case. Like, this would literally not even take up, you wouldn't even be able to see it with your naked eye, and it wouldn't even affect the electrical consumption in any costly fashion at all.
It still seems like IOTA would work without this.
Oh yeah, like IOTA already works without it. There is no doubt IOTA already outperforms all other public distributed ledgers. We already achieved over 400 confirmed transactions per second, and that was just a optimization test. It wasn't even a test to see, hey, how much can we get up to with these 180 nodes? It was just to optimize the client. So it was just experimental. In IOTA, like I mentioned, there is no fundamental limit. So we see thousands of transactions per second being a reality way before any hardware component comes into the picture.
I just question how scientifically understood such a strange and alien novel system like IOTA is, and how sure we can be of its security properties.
Sure. I completely understand that concern. But to those people that have that concern, I would simply tell them to read the white paper, play around with the system, read the code, and you will, like in the beginning, there is some, I would say, cognitive dissonance, because it seems kind of too good to be true, and you're still stuck in the blockchain mentality because that's the architecture that you're used to. So in the beginning, it seems like, hey, this allows for double spends. Hey, this doesn't make complete sense to me. But as you dig a bit deeper and you get over those kind of biases, you realize that IOTA is extremely simple. It's extremely basic and straightforward. So it's not like we have developed this insanely complex system. IOTA is way simpler, in my opinion, than a blockchain architecture. It's way more straightforward and way more efficient as a result of that. And again, I hate to appeal to authority, but if I were to, I would also point to the fact that other people, very intelligent people that I respect, have come up with this idea independently or as inspired by us, and continue to do research on it, because it is quite straightforward when you stop thinking in blockchain terms and start thinking about, hey, this is actually a new architecture, but it's very simple.
Can you be specific about what idea other people are taking up and who those people are?
Oh yeah, for sure. A few months after we began development on IOTA, Sergio Demian Lerner, the CTO of Rootstock, he came up with this concept called DAG coin, Directed Acyclic Graph coin. And it was a white paper. It had a lot of the same ideas. He didn't go to the extreme length that we did. He still had blocks in his DAG, whereas we said, fuck those blocks. We don't want any bottlenecks whatsoever. But he did it independently. He was not aware of our effort at this point. So he's one guy. You have the Spectra researchers in Israel working on a block DAG white paper. And I want to say that when you show the white paper to academics, when you show the white paper to blockchain enthusiasts, in the beginning they may be skeptical, but so far the reception that we've got over the last 2 years has, I would say 95% of them has been like, holy shit, this is brilliant. This actually works. And I think that's why the quick adoption has occurred.
How do you query the Tangle? How do you find a piece of information in there? And where is it all stored?
Oh, yeah. So this is very similar to the blockchain. It's not that alien from the blockchain. Like we have Tangle explorers. I can actually link you to them afterwards so you can check them out. It's just the same process as in a blockchain. But the biggest difference is that, okay, so let me ask you this. Are you familiar with the CAP theorem, the consistency, availability, partition, tolerance theorem?
Yes.
Okay, perfect.
Let's go through it for the audience, though.
For sure. So the CAP theorem, and this is a very high-level, simple description. If you think of databases, let's say we have 10 databases, and you want to ensure that all of them have the exact same data. The latest write of the data is consistent across all of the databases. That is consistency part of it. That's the C of the CAP theorem. The availability is the ability to query this data at any time and check that, hey, yeah, indeed, the data is consistent across all of these databases. The P is standing for partition tolerance. So that means that if 5 of the databases were connected to some meshnet while 5 of them were connected to another meshnet, then that's a partition or 2 partitions. And there is no way for you in the partition A to confirm that partition B is still consistent with partition A, because you're no longer connected. So it's very straightforward in that regard. And in blockchain, you have this global state. So blockchains enforce this global state in order to guarantee that the consistency across the ledger or the databases in my example here are indeed consistent, right? And you have the availability. You can sync to the network whenever you want to. But a blockchain is partition intolerant in the sense that if you disconnect a part of the network and continue to do transactions, then you end up on a fork that is no longer compatible or consistent with the other ones. So blockchains tend to be consistency and availability and very bad on the partition tolerant part. Whereas IOTA, we favor partition tolerance and availability, whereas the consistency is eventual. The beauty of this is that it makes the IOTA network a lot more malleable, a lot more flexible, and this is extremely important in the